Hi, I'm the presenter Dongjae from Seoul National University. The title of this research is Rise-based trajectory tracking control of an aerial manipulator under uncertainty. The presentation will be composed of 6 sections in total, and I will start with introduction. To introduce motivation of this research, as can be found in below videos showing applications of aerial manipulator, an aerial manipulator which consists of a multi-rotor and a robotic arm has been a popular research platform. However, despite its vast potential and various applications, controller design remains a challenging problem. The challenges can be summarized as the following 3. First, couple dynamics between a multi-rotor and a robotic arm. Second, underactuatedness of a multi-rotor. And lastly, model uncertainty and disturbance. The bottom right figure briefly shows underactuatedness of a multi-rotor. Since rotating axes of all 4 rotors are parallel, for the quad rotor to accelerate to the right, it has to tilt its whole body to the right. In other words, it cannot generate force in body XY plane. The objective of this research is to develop a robust adaptive controller based on RISE, which is an abbreviation for Robust Integral of the Sign of the Error, for an aerial manipulator guaranteeing exponential stability under uncertainty. We claim our contribution as follows. First, reformulation of the full dynamics of an aerial manipulator for the ease of controller design and analysis. Second, asymptotic stability analysis with consideration of underactuatedness of the nominal closed-loop aerial manipulator system. And lastly, the first approach to apply rise control to the aerial manipulator, guaranteeing exponential stability under uncertainty. Since the objective of this research is about robust adaptive controller design for an aerial manipulator, we examined studies on such topic. To the best of our knowledge, error convergence to zero under uncertainty and disturbance has not been shown with existing controllers for an aerial manipulator. The below table showed some of the related work, and none of existing work on controller design for an aerial manipulator satisfy the 3 criteria, which are whether they consider first, couple dynamics between a multi-rotor and a robotic arm, second, underactuatedness in stability analysis, and third, error convergence to zero in the presence of uncertainty. From this part, dynamic model of an aerial manipulator will be explained. We take a generalized coordinate and control input as follows. First, a generalized coordinate Q is taken as the center of mass position of an aerial manipulator P subscript C, GYX Euler angles of a multi-rotor phi, and joint angles of a robotic arm theta. The right figure shows one prototype of an aerial manipulator, but we did not assume any particular number of joints. Control input U is taken as multi-rotor's total thrust in body z-axis, T, multi-rotor's torque in body coordinate tau subscript phi, and joint torques of the robotic arm tau subscript theta. Equations of motion can be derived as in the reference 1. Translational dynamics in rotational dynamics can be derived in a decoupled fashion. To compactly write rotational dynamics, we use notation R to denote both phi and theta. Delta with subscript T and R are disturbance in translation and rotation. Based on the derived dynamics, this part introduces controller design. In contrast to conventional multi-rotor dynamics, the total thrust T affects the rotational dynamics due to the non-zero term S transpose RB3 in the input matrix. Therefore, if one naively applies inner loop orientation control and outer loop translation control strategy, which is widely used for controlling multi-rotors, the total thrust T should act as a disturbance to the rotational dynamics. To overcome this issue, we decompose the dynamics into underactuated and fully actuated subsystems as in equations 1 and 2. The configuration of the underactuated part is taken as Q subscript U, whereas that of the fully actuated part is taken as Q subscript F. Since Q subscript U is just the first 2 elements of the P subscript C, which is the position of the center of mass of the aerial manipulator, the reformulated dynamics can be easily obtained. We then modify the dynamics to consider underactuatedness. To control the underactuated subsystem in equation 1a, desired roll and pitch angles are used. For this purpose, we divide the input matrix B subscript U into psi and phi, where psi is a 2 by 2 matrix, only a function of yaw angle, and phi is a 2 by 1 vector, only a function of roll and pitch angles. Then we add and subtract the term t bar times psi times phi subscript d as in equation 2a. By doing this, we can now consider the term phi subscript d to be a control input for the underactuated subsystem as marked in red in equation 2a. For the ease and uniformity of controller design, we consider the following form of dynamics in equation 1. MFU matrices and vectors for both underactuated and fully actuated dynamics can be derived from the equations in the previous slide. For example, M is defined from mass matrices, and F is defined to include all nonlinear and additive disturbance terms in the dynamics. We use the hat symbol to denote a variable with nominal physical parameters. To have well-defined dynamics, we impose two assumptions, which are roll and pitch angles of the multi-rotor base are bounded between minus pi over 2 and pi over 2, and the total thrust T is not zero. Note that these are widely used assumptions in quadrotor controller design. As discussed earlier, the control input of the underactuated part, which is U subscript U, is transformed into roll and pitch desired angles by solving U subscript U equals T bar times psi times phi subscript D. Rise controller itself can guarantee exponential stability without the help of nominal controller. However, since rise controller relies solely on error integrals, initial performance can be degraded, particularly for hovering control where unceasing non-zero thrust is required. Therefore, nominal control is designed for better initial performance. Similar to reference 1 and 2, a rise controller is designed for both the underactuated and fully actuated parts. Nominal controller is designed to guarantee exponential stability of each subsystem, and rise controller is introduced in the right. Note that as the name indicates, rise controller utilizes sign of the error along with the error itself. This part is about stability analysis. To analyze nominal closed-loop system, 3 blocks should be considered at once. The 3 blocks are nominal dynamics, nominal controller, and mapping between control input for underactuated part to roll pitch desired angles. We claim the following theorem, which states asymptotic stability of the nominal closed-loop system. Interconnection between underactuated and fully actuated subsystems exists since the whole aerial manipulator is underactuated, and this can be found from the term phi minus phi subscript d in equation 1a and 2a. To take this into account in stability analysis, we adopt the stability theorem for a cascaded system, and detailed proof can be found in the paper. Now, to analyze the actual closed-loop system, we first analyze the following virtual system and control input in equation 2, since the underactuated and fully actuated parts share the same structure as in equation 1. State is defined as the generalized coordinate q and its time derivative q dot, and input is u. Input consists of nominal control input u subscript n and robust feedback control input u subscript r, which are defined in equations 2b and 2c. Now we claim the following theorem. For the positive definite diagonal gain matrices satisfying the written condition, the closed-loop system of 2 is semi-globally exponentially stable. Proof of this theorem can also be found in the paper. Finally, we present a stability result for the actual closed-loop system for an aerial manipulator. By combining a nominal controller and a rise controller as in the below figure, we can achieve exponential stability in the presence of uncertainty. Due to the use of Euler angles, only local result is obtained, but by taking larger control gains, the region of attraction can still be arbitrarily expanded inside the set where Euler angles are well defined. Here, we assume that external disturbance and their time derivatives are bounded, and the gain matrices satisfy the written condition. We now present simulation results. The first simulation scenario is to stabilize at the origin while swinging the robotic arm in the presence of uncertainty. Parametric uncertainty on physical parameters of mass and moment of inertia is given as 30%, and time-varying disturbance is provided. Sinusoidal disturbance of magnitude 1 is added in translational motion, where total mass of the robot is about 3 kg. We compare the result with existing two controllers, which are based on adaptive sliding mode control and nonlinear disturbance observer, which are abbreviated as ASMC and DOB. Adaptive sliding mode controller can guarantee asymptotic stability only in the presence of slowly varying disturbance, and the disturbance observer-based controller can guarantee uniform boundedness in the presence of time-varying disturbance, but not convergence. In all figures, red dotted lines are the result from DOB, and blue dashed single dotted lines are those from ASMC. The black dashed lines denote the result from the proposed rise controller. The left figure shows XY position trajectories. One can observe that the proposed controller outperforms the other two in terms of convergence to the origin. Time history of error signals also shows effectiveness of the proposed controller compared to the other two. Control inputs obtained during the simulation are depicted in the right figure. Although initial peaking phenomenon is observed for DOB, which is a feature of a disturbance observer, reasonable control inputs are generated from all three controllers afterwards. The second simulation setting is to track a circular trajectory with radius 1. The same amount of uncertainty is provided to the system, and the desired trajectory of the robotic arm is also identical. As can be found in the left XY plane projected figure, the proposed controller shows the best circle shape of radius 1. Time histories of position and orientation error signals also validate the proposed controller's performance. Time histories of the three controllers' control inputs are plotted in the right. The ziggling signals in blue is from the ASMC, which is widely known limitation of naive sliding mode controllers. Now, this part is about conclusion. In all simulation results, the proposed rise method outperforms the other comparing two in error convergence. As a future work, we expect to implement the proposed controller to an actual aerial manipulator and perform various applications where precision is required. The below video shows our preliminary result. We only implemented the nominal controller and not yet the rise controller. Robustness in the presence of disturbance and uncertainty will be tested for the proposed rise controller. Thank you for listening to my presentation. If you have any questions, please feel free to ask or send an email. Thank you.